Hello and welcome to episode 17 of the Minimapper series. Today we're going to look at testing the motor prototype board and the software that goes with it. I'm dressed up in winter clothes because I'm in the shed in our garden and it's definitely not very much above freezing outside. The garden's full of snow, so it's a little bit cold. Can't quite see my breath, but I could earlier. So we're going to do this in 3 bits. We're going to test the motor board electronics, then we're going to test the software, and then we're going to test the two together. And the first 2 bits we're going to do using the Analog Discovery 2, this thing, which will allow us with the electronics to drive the electronics using the Analog Discovery user interface. And then when we're testing the software on the Nucleo board, we'll be able to look at the signals that it's generating and generate some fake signals for the motor encoder and the motor coil current. And then once both of those are working, we'll put things together. Now, I've done the first 2 bits of this already before, so it ought to just work. The 3rd bit, testing the 2 things together, I've not done at all yet. So this is going to be a live test. Anyway, let's get started. Okay, here's the setup for the first set of experiments where we're going to test the electronics. I've got the robot chassis clamped to the table. I've done it this way so you can see one of the wheels, so you'll be able to see it turning around. I've got the motor controller board on top. The 5-volt supply for the motor controller board is attached to a normal wall wart power supply. This motor, the power connections for it are just here. They're behind this other tangle of cables, so you can't really see it. And the Analog Discovery is over here. It's attached to the PC by a USB cable. And then there are these connections here between the motor controller board and the Analog Discovery 2. And the Analog Discovery has power supplies in it. So 3.3 volts power is supplied to the motor controller board here, and there's a ground at the other end. The 82 has an analog scope input, and so one of the connections here is the motor coil current sense output from the motor board. The 82 has digital logic analyzer functionality, so there's a pulse output from the motor encoder that goes to one of the channels on that. And the 82 can also do logic level pattern generation. So there are 2 connections, the green and the pink wires, I don't know if you can see the colors here, that go to the motor controller inputs here. So let me switch to a view where we can see both the live video of the motor board and the waveforms application, which is the software side of the 82. And what we have here, we're looking at the pattern generator, which is the logic level function generator, basically. And we've got these 2 channels, channel 0, pink, channel 1, green. And channel 0 is connected to one of the motor inputs on the board, and channel 1 is connected to the other. And at the moment, both inputs are steady high, which switches the motor controller off. If I change this one so that it's now PWMing at 90%, you can see the wheels start to turn around, turning. You can also, if you look carefully here, see the motor encoder disc turning around much more quickly. There's a gearbox, which is it's a 48-to-1 gearbox, so the motor encoder disc turns around 48 times faster than the wheel. And for sure, you can make it go faster. Ooh. And for sure, now the camera can't keep up, so you can't tell which way around it's going. So we have control over the speed of this thing. And if we switch them back to both high, it stops, and we can make it go in the... We should be able to make it go in the other direction, but it doesn't seem to be working. Why is that? There we go. Now it's going in the other direction. Don't know why that was. Maybe there's some... there's some difference between the forward and backwards. There's a bit of a threshold. I hadn't noticed that before. There may just be something in the way. I might have to experiment with that a bit. But you can make it go forwards and backwards by controlling the PWM duty cycle on here. And now that we've got it going forwards and backwards, let's take a look at some of the other things. So the motor pulse input, if we switch this on, we see that there's a waveform on this, and we can see the width of this is about 3.2 milliseconds. If we change the motor rate so that it's going a bit faster, and then take a look at this, you see the pulse width is reduced to about a millisecond. So this pulse input gives you a way to measure the speed of the thing. And this input's pretty easy to calibrate because you know the diameter of the wheel, you know the spacing of the teeth on the motor encoder disc, and so you can relate the frequency of this pulse train to how fast the wheel is going around. The other input that we have is this analog measurement for the motor coil current, and so this is a 50 millisecond division here, and you can see there's some voltage here. This testing is basically just a smoke test to make sure that this thing works. So here we've got about 0.4 volts on this. I'll talk about the noise and the oscillations on this in a minute. If we increase the speed to say 50%, we see it's gone up to 0.6, 0.65. My suspicion is that this stuff here, these oscillations, are the 20 kilohertz switching frequency for the PWM output. It turns out it doesn't look like it on this FFT. So I'm going to have to experiment and see what that is. So there's the main signal there seems to be 4 kilohertz, and I can't remember. I thought that I was using about 20 kilohertz for the PWM frequency, but I might have switched it down for reasons to do with looking at these signals on the AD2. But this, I mean, you can see it's really pretty solid. So there's definitely some source of these oscillations coming probably from the motor controller. But it's not actually much of a bother because we can sample this signal in software quite quickly and average it. And it's I don't think kind of low pass filtering out these oscillations in software is going to be much of a problem. So the electronics seems to work. We can make the motor go back and forth. There's this funny thing with the threshold in one direction that I need to experiment with. We have a motor encoder pulse train that allows us to measure the speed of the motor, and we have a signal that varies with the speed of the motor that should be related to the torque. I can show you one other thing as well. So if we get the motor running quite quickly, and then we look at this torque curve. If I stick my finger on here, so that you can see that the torque curve goes up and down as the motor's working harder or less hard to turn. There's one other thing from the pulse train as well. You might notice that this pulse train is not completely steady, even though the motor is nominally running at a constant rate. And that's probably due to the fact that the mounting of this encoder disc is not perfectly perpendicular to the motor shaft. I had some trouble getting it on, and I've got a better idea of how to do it in future. And some of the variability in this pulse train definitely comes from this thing not being mounted quite straight. Anyway, so there's the electronics, and this kind of worked pretty much first time, which I was pleased with. So let's go on to looking at the software now, which means I need to change things around. So now we're going to do the second part of this, which is testing the software that talks to the motor board. And the software is running on this STM32 Nucleo board. It's connected to the Analog Discovery 2, as before. This time we're using the Analog Discovery 2 the other way around, more or less. For testing the electronics, we use the logic pattern generator on the 82 to drive the motor controller. In this case, we're generating those signals on the Nucleo board, and so we're going to use the logic analyzer inputs on the 82 to see what they look like. And similarly, last time we were using the 82 to measure a pulse output from the motor board and to measure the motor coil current signal from the motor board. This time we're going to use the 82 to generate synthetic signals for those things, so an encoder pulse train and some values for the torque coil current signals, and we're gonna check that we can measure those with the software. So we're gonna do this using a terminal application. So this is Minicom, and it's connected to the virtual COM port on the Nucleo board, and the Nucleo board is running a command shell application that has some commands for testing the motor stuff. So the first thing to look at is the logic outputs from the PWM channels on the Nucleo board that control the motors. So these two inputs on this is the logic analyzer on the 82, so these are inputs to the 82, and you can see that they're both high at the moment, which makes the motor be off. If I tell the motor to run at 10% forward, then you can see that one channel switches to having a PWM signal at about 10% duty cycle, and if I say forward 50, switches to a 50% duty cycle. I say stop. It takes a little while for the 82 to pick up the constant signal, but it goes back to both being high. And if I say reverse 25, you can see that the PWM signal switches over to the other channel. And this is the way that you drive this Toshiba motor controller chip that I'm using to make the motor go back and forth. So this bit of the software works, and it's pretty clear that it's okay. The next thing we can do is we can look at the torque values. So the values read by the ADC in the STM32 that we're using to monitor the motor coil current. And the way this is set up in the software is that there's a timer that triggers ADC conversions, and then those are transferred into a buffer for handling by DMA. And this is set up so that you can do this for the two motor channels at once, for the left and the right motors. And so this software has a thing to periodically read this ADC. And here I'm using the function generator on the 82, and here it's just generating a DC signal. Here it's 0 volts. If I switch it up to 1 volt, you'll see the values from the ADC change, and change again. And so this gives some confidence that these measurements in the software are actually working. And the software has various features to do with calibration of this stuff, so converting the ADC counts to motor coil currents here, and then eventually to torque values. That'll require some experiments to calibrate that. And it has some stuff to do with how you average these things. So that part of the software works as well. And again, there's more to it than it looks like here. I actually ended up writing 3 blog articles about how you do this timer plus ADC plus DMA thing on a STM32. So we've got that, and then the other thing is that we can look at the motor encoder inputs. So again, we've got this kind of thing where it does regular measurements. I think this is stuck at some previous values I was measuring, but let's switch the pulse generator on, and let's change this. And you can see that the time between the edges, so this is counting edges in this square wave signal. So it's actually twice as fast as the frequency you set here. But this gives you a way of measuring the speed of the wheel's turning, and this is just based on a nominal diameter of the wheel. So again, this is something that this is a demonstration that this bit of the software is working. And so I really like this way of testing software and embedded hardware, or embedded software and the hardware it runs on, where you do a little test of the hardware with simulated inputs, and then you do a test of the software with using something like the AD2 to simulate the hardware side. And it gives really good confidence that things are working, which means that I can now try putting everything together. So that's what we'll do next. So now we come to the fun bit, which I've not tried before. So again, I've got the robot chassis clamped to the table. I've got the 5-volt power from the wall-wart power supply connected to the motor controller board. And now I've got the motor controller board connected to the Nucleo. And so there's a ground connection between the two. There's 3.3 volt power being supplied from the Nucleo board. There are the two connections for the motor controller PWM channels. There's one channel for the motor encoder pulse output, and there's one analog connection, which you can't really see, it's over here, for the motor coil sense current connection. And so, as before, we use the same command shell application, and it works. And we can make it go the other way. Something's gone a bit funny with the command shell, but it doesn't matter too much. And if we set it going forward again, so there's definitely an asymmetry between the forwards and backwards, and I need to figure out why that is. I don't know if it's, I can't imagine it's anything to do with the electronics. The electronics is pretty symmetrical. It might just be that the motor's a bit duff. And then we can look at the motor encoder speed information. So here you can see there's some variation in the pulse times. If we make the motor go faster, then the pulse times go down, and I need to look at these speed values and see how reasonable they are. You can see the speed fluctuates a bit, and some of that may be to do with the motor, some of it may be to do with the motor encoder disc not being mounted terribly well. It's hard to know. So let's stop that. Oops. And now we can look at the motor coil current measurement. So I'm not sure I believe these current values yet. I've not really looked properly at the calibration of this, but you see there are the ADC measurements are coming in okay, and if we reduce the speed, or let's increase the speed, let's make it more fun. So if we go forward 75, you can see the measured current jumps up right away. If we switch back to 25, goes back down. I'm pretty pleased with that. I think that works okay. So all in all, I'm pretty happy with that. The electronics worked more or less first time. Developing the software took a bit longer than I was hoping it would, mostly because of the approach I'm taking, and I'm learning lots of new things while I do this. So I've been doing quite a lot of test-driven development for this, which is something I've done a bit before, but mostly in Python. And so doing it with embedded C++ is a new thing. C++ is sort of new. I used to write a lot of C++, but that was 15, 20 years ago, and C++ has changed quite a lot. And so I'm trying to learn some of the things that people call modern C++ as I go along doing this. and then learning the STM32 architecture. And the STM32 chips they're nice. They have a good range of peripherals. They're kind of the vanilla ARM microcontrollers. They do have some funny things though, and it's very easy to get into a state where you've not switched on one of the many switches that you need to switch on to get a particular peripheral working. You need to switch the clocks on, you need to switch the peripheral on, you need to switch the clock for the DMA controller on if you're doing DMA, and so on. And so that took me a little while to get going. The next thing to do is to look at doing some control on the motor board. So a constant speed PID controller is the first thing I'm going to try. And I want to make a kind of independent way of measuring the motor speed. And so I'm going to make an optical tachograph from, I think I've got a webcam lying around and I can do that with. So that will probably be the next thing I do. So I'll see you then for that. I'm not sure when. These things are taking me a bit longer than I'd hoped, and I've got other projects on the go as well. But it's kind of fun, and it's very satisfying when this sort of stuff works. And I really do think the 82 is a good little tool. I mean, for a box that's the size of your hand, you have admittedly fairly low quality scope, function generator, logic analyzer, pattern generator, power supplies. It's got some software for doing spectrum analysis. I think that you can even do very simple network analysis with it too. So it's really great. And instead of having a rack full of kind of high-end lab equipment for hobbyist stuff, it's really good. So I really like that, and I really rate it. Anyway, that's all for now.